Hi. Thank you, Biscala, for the invitation. It's a real pleasure. I hope you're very energetic and not too sleepy after the lunch, which was very good, by the way. And before I dive into the talk, I want to ask a little question, because we're all functional programmers, I hope. And what is functional programming good for or good at? Well, to me, it's two things. First, functional programming is very good at modeling complex data models. We have immutability, we have algebraic data types, we have pattern matching, we have all kinds of goodies that helps us define very complex and very sensible domain models. And next, functional programming is also very good at modeling effects. We have had a few talks about ZO, Katz effects. It's all the rage right now around modeling effects. And in the end, when using functional programming, we build applications like tiny and nice little boxes. Inside the box, everything is pure. There is no side effects. Everything is very amenable to reasoning, mathematical reasoning. And we try to push everything that is impure to the sides of the box. Maybe that's why we call them side effects. But the problem is that these boxes, they are completely useless if they are not able to, if we are not able to put data in and out the boxes, right? If your program doesn't do any side effects, or if it doesn't communicate with the outside world, it's completely useless. And therefore, in every single project we work on, every real-world project, we have to manually write code for serializing data in various formats, for example, JSON or Avro, protocol buffers, Thrift, and probably 3 other flavors of JSON, because we love JSON. But also for validating user input, for reading configuration files, accessing data in database, pretty-printing, generating random data for property-based tests, pretty-printing, comparing values, and so on and so forth. That's a lot of code we have to write. And this code is really repetitive. We do that for every project. It's really mechanical. We don't have to think about it. And it brings absolutely no business value. The business value is the business logic. All that crap we have to write in order to make our program usable, it has no value. We have to do that. We have to write it in order for our applications to have a value, but the value is not there. So can we do better? Well, as Scala developers, our reflex would be to say, well, let the compiler write this code for us. And in fact, we have many, many goodies in Scala for compile time derivation. We have the generic solutions. We can go plain old macros or use Scala meta. We also, of course, can use Shapeless for that, or Magnolia. Say hello to John for that. Or Scala Z deriving. Probably you're less familiar with that one. And also, we have specialized solutions for different specific problems. For serialization, we have Cersei, Skodec, Avrofores. But also for generating data, we have ScalaCheck, ScalaCheck Shapeless, and so on and so forth. But the problem with these solutions is that we end up with many different APIs for doing this kind of stuff. We don't have a unified framework for that. Some of them are not really easy to customize. For example, in Cersei, you can customize the way the field names are written. But, for example, if you use Shapeless, it's very difficult to customize the way you produce or read JSON. Sometimes it slows down compilation, especially in the Shapeless case. And the error messages are not always very friendly. So it's a solution, but it's not really really convenient all the time. But the convenience is not the worst problem with that. In fact, when we derive at compile time our serialization protocols, we are binding our ADTs to the way we format data on the wire. And therefore, it makes our ADTs very difficult to evolve. Because once you've written your ADT into JSON and send it into the wire, you're not in control of it anymore. You cannot change it. But if the business requirement change, you want to change your ADT. And you end up with something I call the evolution problem. So let's imagine a very simple distributed system where we have only 2 nodes. And they communicate with each other by sending JSON messages. And in that case, the JSON message contains a field called name. Now imagine we build a new version of this application, and we decide to change this field to first name. What happens if we deploy this new version on our cluster? Let's say we first deploy it on the node 0. Well, we've deployed it on the node 0. So now the node 0, when it receives a message from node 1, it cannot understand it anymore because the node 1 is still on version 1, and so it sends messages with the field called name. That's a backward compatibility problem. Our new version is not backward compatible. And of course, the other way around is true. The new node will send messages with first name, and the old node is not able to understand that because it's not forward compatible with the new version. So that's the evolution problem. Has anybody run into that problem in production? Yeah, almost everybody. So it's very sad, because we end up with poor solutions to that problems. Sometimes what I've did in the past was to keep all versions of my ADTs in the code base just to derive serializers or deserializers from them. And you will end up with a very dirty domain model with old versions laying around. And also, another solution would be to write manually readers for the old versions, for example. But that's not really satisfying. So let's try to solve that problem. The solution we are looking for will need to build upon an abstraction over the structure of data, because that's what we want to track the change of. And the very important part is that this abstraction must be decoupled from our ADTs, so that we can evolve the ADTs and the abstraction differently. And of course, we still don't want to write all this code manually, so from this new abstraction, we need to be able to derive operations, or type classes, if you prefer. And then, once we have this abstraction, we will be able to solve the evolution problem on that abstraction. This abstraction already exists, and it's called a schema. And from now, I will present you a library I'm working on called Schema Set. And I will briefly show you how it works. So Schema Set builds upon the idea of algebraic data types, and especially on the A of ADT, the algebraic word. It turns out that all the algebraic data types we know and love can in fact be expressed using only 3 components. The unit type, which is unit, it has only 1 value. The binary sum, we can use either for that. And the binary product, we can use the tuple 2. So how does it work? Let's say we want to represent the bit type. A bit has only 2 possible values, 0 or 1. And I can say a bit is like either unit. And to convince you that these are equivalent, let's do a little bit of counting. Unit is a type that has only 1 inhabitant, right? It's a unit value. Either AB is a type that has as many inhabitants as there are inhabitants in A plus inhabitants in B. So either unit has 1 plus 1 inhabitants, that's 2. That's the same number of inhabitants as the bit type. So there must be a correspondence from bit to either unit. Similarly with the product, let's say we want to define a byte type. We can do that by saying this is this big, ugly, nested product here. So again, let's do a little bit of counting. Product, it's a product. So a product has as many inhabitants, a product AB has as many inhabitants as there are in A multiplied by the number of inhabitants of B. So this pair of bits has 2 times 2 equals 4 inhabitants. If I pair it with bit, it's 2 times 4, it's 8, and so on. I end up with 256, and that's as many as there are bytes. So it's very ugly, but there must be a correspondence between the two. And we can keep on going like that forever. For example, option is equivalent to either unit. Option of A is equivalent to either unit or A. Unit will be known, and A will be A, or some A. We also can build this kind of equivalence for recursive types, like list, but it becomes more difficult to express that in Scala with a type alias in Scala, because we are not allowed in a type alias to have a recursive reference to the type itself. But just as a matter of explanation, I could say the list of A is equivalent to either unit, that would be the empty list, or a pair of A and a list of A, the head and the tail. And in fact, you can end up with a trick to write that in Scala, but let's forget about it because the syntax is pretty ugly. And of course, this worked for simple types, but it also worked for our beloved case class and seal trait. A case class is merely a product. So for example, here, this customer case class can be expressed or equivalent to this tuple. It has 3 fields, string, string, int, so it's equivalent to a pair of string and pair of string int. And similarly, for seal trait, it's equivalent to sums, to eithers. So for example, here, the user seal trait is equivalent to either an admin or a customer. Right? So that's all we need to express every possible ADT. Unit, a binary sum, and a binary product. But of course, doing so wouldn't be very convenient in a real-world setting. In a real-world setting, we don't want to define bytes with this ugly nested product I showed earlier. So it would be convenient to have a way to represent primitive types. We also need a way to represent sequences without the very ugly syntax we saw in the previous slide. And most of the time, especially when it comes to serialization, we are interested in the field's names. So we would need to define this record and union abstractions. A record is just a product whose members have a name, and a union is the same for the sums. And finally, thanks to something called an isomorphism, which is merely an equivalence, we are able to tie this representation, ugly representation, to our concrete types. For example, let's get back to our schema of bit. So in Schema Set, you would define the schema of bit like that. Say it's unit or unit. So this is the schema for either unit. And if we want to build the schema of Boolean, which is a real type in the Scala library, you would just say, OK, a Boolean is equivalent to a bit, and let me prove that. I build an isomorphism between either unit, and Boolean. by just providing two functions that goes both ways. I could decide that left would be true and right would be false, and so when I get a bit, or either unit, I fold it to get a Boolean, and then when I get a Boolean, I decide if it's true, I return left, if it's false, I return a right unit or a left unit. So that's it. Now I have everything I need to build a schema for my ADTs, my concrete ADTs. Well, actually, it's a little bit more complicated in the Schema Set library because we are using a technique called recursion schemes. So before diving in, was a little bit familiar with recursion schemes. OK, so I need to explain a little bit. It's not really important for the rest of the talk, but it's something I love, so I cannot avoid explaining it. Recursion schemes is just a technique to decouple recursive traversal of a structure from what you do with each of its elements. It's just that. When you use recursion schemes, you define your structure in a certain way that makes it amenable to the technique. And once you've done that, everything you want to do with your structure is just a matter of saying, OK, when I have this kind of node, I do that. When I have this kind of node, I do that, and so on. You end up writing only pattern matchings. And it works by replacing in your structure, for example, say we have a tree. I have a sealed tree and a node, which is a case class containing two trees for left and right branches. This is not amenable to recursion schemes. What I need to do first is to replace this recursive reference by a type parameter. And then I'm good. That's the classical recursion schemes. Here, we need to go one kind higher because we need to know that the left branch is about an A and the right branch is about a B. And we end up with this encoding here. So it's not the full schema F ADT, but the important part. So for a sum, our either, I would say, OK, the left talks about an A, the right talks about a B, and therefore this sum, SAB, is in fact the schema for A or B. And similarly for products, the left is about an A, the right is about a B, and the whole thing is the schema of pair AB. That's it. So we have our abstraction. It's a little bit complicated, but that's pretty much fine. Now what we need to do is to be able to derive operations from these abstractions, because again, we don't want to write all the serialization code by hand every time. So by operation, I mean something that is sometimes a type class, but it's not always the case. For example, type serialization is not really a type class because it doesn't really have laws. But in summary, an operation of A is something that resembles a function that either takes an A or returns an A or both. And so in the following, I will just summarize that with f of A. It can be a JSON encoder, it can be an ordering, it can be a show, it can be whatever type class you want. So how do I derive an F from a schema? And what it means to derive? Well, it means that given a schema for A, for any possible A, I want to get the corresponding f of A. And because it's a for any A, this, in fact, is what we call a natural transformation. So deriving an operation or a type class from a schema is just being able to build this natural transformation from schema to F. And how we do that? Well, that's where recursion schemes come into play. And it's actually fairly simple. At the leaves of our schema, we have schemas for primitive types, integers, strings, booleans, and so on. So we should be able to build f of int, f of string, f of boolean quite easily. And what the Recursion Schemes API does, when we give it a schema, it will first go down to the leaves, transform the leaves into a corresponding f, and then it will climb the tree back up. So when it encounters, for example, a product term, it will have a product of f of a and f of b, and it will just have to produce an f of pair ab out of that. So you see, when I write my derivation, which is not really the point of this presentation, but still, when I write a derivation, all I have to care about is how to mix an f of a and an f of b to come up with an f of ab. That's the power of recursion schemes. And by the way, in the recursion scheme terms, this is called a catamorphism, which is the kind of word that makes you feel very clever. Anyway, so now back to the point of this presentation and solving the evolution problem. To recap, I want to be able to have backward and forward compatible serialization protocols without having to write anything by hand, and more importantly, without having to carry along the old versions of my ADTs in my code base. I must have only one version at a time of my ADTs. And if we squint hard enough, it's just a matter, especially for backward compatibility, of being able to come up with a reader that is able to read the old messages and produce the new ADT out of that. Okay? So here is the naive strategy we used, or we tried, to solve that problem in Schema Set. First, you need to define what is a backward or forward compatible modification of the ADT, because not all the changes you can do on the ADTs will give you backward compatible transformations. Then I will use this new abstraction, the migration or the evolution, if you prefer, to define the schema, some schemas for to define the older versions in terms of the new one. Right? I will say, to get from the previous version to the current version, I added this field to this ADT, for example. Then I will use that to produce new schemas, alternative schemas that will represent the old versions. And finally, from these alternative schemas, I will derive a reader, and that reader hopefully will be able to read the old messages and produce the new ADTs out of that. So, step one, defining what we call the migration steps that ensure backward and forward compatibility. And that's just yet another ADT. For example, I could say I'm allowed to add a field to a record as long as this field has a default value. Because if it doesn't have the default value, you're not backward compatible. I'm also allowed to rename a field as long as the new name is not used in the record, and so on and so forth. You end up with a set of allowed transformations. That's the simple part. Then, the step two, I want to build some kind of changelog of my ADT. I'm starting from, and that's the tricky part, I'm going backward. I'm starting from the current version that I could, I don't know, write by hand or derive at compile time, that's allowed. And then I say, okay, what has changed from version 1 to version 2? Well, I added a field to the schema of person. And again, what changed from version 0 to version 1? When I took the version 0 and I renamed the field from name to username. So you see, it's really a changelog or the git history of my ADT, but in reverse. So that's cool. But this must be a schema, right? This API must produce a schema of the current version of the person ADT. So let's imagine we do that by hand. That is, instead of doing that, we do it by hand. So imagine in that case, I have my person case class, and in the version 2, it has 3 fields: age, username, and email. But as we see here, I added the field age in version 2. So it means that the messages from the version 1 that don't have the field. So in order to be able to read them, what I need to do is inject the default value. That's why I need the default value, by the way. And this is done by just plugging. It shouldn't be called an isomorphism because it's not an isomorphism, but yeah, let's keep things simple. I just do that. I say, OK, this is the representation of the case class in version 1. It only had 2 fields of type strings, so it's a pair of string. And I need to produce a person out of that. And it's very simple. If I get the pair of string, I just inject the default value and build a person case class. And the other way around, I have a person. I must return a pair of string. I just drop the field, and that's it. So that's the manual way. And the big problem with Scala Z was to find a way to do that automatically. But once it's done, I get a schema for person that reads the version 1 messages. All I need to do is to derive a reader from that, and I'm good to go. Schema Z, by the way, doesn't provide a way to detect the version of your message. It's the user responsibility. You can use metadata or header in a message or a special field. That's not our problem. What we provide is a way, once you've decided which version your message is in, to pick the right and express the right reader and pick it. So that's it. We've solved the evolution problem. Aren't we happy? Yeah? No? Maybe? Or just taking a nap after lunch? Well, actually, I've already said that, but it wasn't that easy. Actually, it was really, really hard. It took me like 6 months. And I figured, because we are in Ljubljana, here be dragons. So we found a bunch of problems. First, the fact we use recursion schemes, which was almost mandatory for that project, made our life difficult in order to verify that a migration can apply to a given schema. Because that's the whole point. The recursion scheme representation, with the functor and so on, the type parameter instead of the recursive reference to the type, it makes the structure of your schema invisible from the type level. And so if I give you a schema and I say, I added this field in the schema, the compiler has not enough information to make sure that this field actually is in your schema. So making something type safe because of that was very difficult. So the solution we found was, yeah, more types. We used simply a phantom type that will mimic or mirror the structure, the underlying structure of the schema, but at the type level, so that we could reason about this structure at the type level with typical implicit resolution techniques like in shapeless. And the cool thing with that is that now a migration becomes a function from this new schema with 2 types. Here is the representation, that is the structure of the schema. And here is the type that is represented by the schema, your ADT. And so a migration is just saying, OK, I will go from one representation of A into another one. But I will always keep representing the type A. Which led us to the next problem, that Scala C is not helping at all. Because I've lied a little. This is not really a function. Oops. This is not really a function. It's a dependent function. It means that this new representation, it depends on what was the initial representation, which is a type, and the migration value we are applying. So it's a dependent typing problem. And Scala C doesn't completely do dependent typing. And so in the general case, we weren't able to make Scala C infer this type for us. And because this type is very big, it's really the value of your schema, but at the type level. It's not an option to make the user type it. We absolutely need it to be inferred. And I think we got it right, but there is something in Scala C, at least in Scala 2, that makes it unable to correctly infer it. And at the end, we ended up with very, very big error messages where it boils down to 1 was not equal to 1, which I believe it's false. This statement, I believe it's false. But still, there was not any way to make Scala C, to convince Scala C that we were right. So the solution to that problem was to just give up on generality. Because it works, but only if you apply a migration at the shallowest level. Meaning that you can modify the structure of a record, but you cannot modify the structure of what's beneath it. So you can add a field, remove a field, rename a field to a record, but you cannot do the same to a field's value. So what we decided was to say to the users, okay, if you want to, you still can define big schemas where you define all your model in one single schema. But if you need to do migrations, you have to split it in smaller schemas and build the big one in terms of the smaller ones. And that works. So that's cool. We're almost there. But by doing so, because your new big schema is just a function call where you pass parameters that are the small schemas, if you make a migration to the smaller one, so you define version 1 of the smaller one. If you want version 1 of the big one, you have to call your function again. And so in the general case, for migrations, you end up rewriting your old model, your old schema, for every version. And that's exactly what we wanted to avoid. So it was big frustration. And grumpy cat picture, and so on. And the solution to that problem is pretty funny. We defined what we call a version. And a version is basically a H list, or if you want, it's a dependency graph. You put, it works like a stack, where you put functions. At the bottom of the stack, you put functions that produce the schemas, the smallest schemas you have, the ones that doesn't depend on any other. And the version class allows you to put something else on the stack that is a function that will take parameters, as long as these parameters are already produced by some function below on the stack. So for example, if I have a person class that contains a field of type user, I first need to put on my stack the function that produces the schema for user, and then I'm allowed to put on top of that a function that takes the schema for user and produces the schema for person. And then, once I have my stack, since it's only functions, not applied, I can also say, okay, so my current version is that, it's that stack. My version 1 is the same stack, but at this point, you've modified the function by composing a migration on top of that. That works because we haven't called the function yet. And finally, when you request the schema for person at version 1, it will apply the functions in the right order, propagate every migrations below from the stack up, and you will get the person that contains the users that will be migrated from version 1. That's probably a little too much, but let's take a look at what it looks in the real case. So we have this current object that allows us to build our current version, and we just stack schemas on top of one another. Again, it's reversed. The bottom of the stack is at the top, and so on, but that's it. So my first schema, the bottom of my stack, is the schema for user. I build the schema using the API, blah, blah, blah. And then I can stack on top of it a function that takes a user, a schema for user, and build a schema for person. That's my current version. Now, what I can do is say, OK, I will migrate this user to get to version 1. And that's just it. I take the current version, I migrate user, and I say, OK, I added this field, a name, with this default value. And that's it. Now, if I take my version 0 and I look at person, I will get a person that contains a migrated user, a user that doesn't have this field. And that's it. This time, the evolution problem is solved. We have achieved minimal boilerplate that allow you to define schemas, migrate schemas from version to version, and still not write any code for serialization, except the code that will read the version in the message and pick the right reader, because that's your responsibility. Aren't we happy? I am happy. And on top of that, schemas, as I said, give you many, many things for free. You can have random data generators. That's the actual syntax in Schema Set. But you get a schema to gen, and you get a gen for your case class. You can have pretty much any type class, EQ, ordering, show. You can also do more crazy things like building UIs on top of your schemas. So if you are missing a front-end developer in your team, you can say, OK, I will build my UI from the schema, and if I change the schema, the UI will reflect this change automatically, because I've built it from the schema. You can have many serialization protocols, like Avro. You can also use that to build SQL queries and migrations. You could derive from the Scala code that define the migration the SQL scripts that will migrate your database accordingly. And you can even go completely crazy and say, but why on earth do I need my ADTs? I could do everything with schemas. And for example, and that's something I didn't do with Schema Set, but William can talk you about the project where we did something similar. When you build a data pipeline on mere schemas, you end up with one piece of code that is able to handle every possible data source, as long as you provide a schema for it. So you develop your pipeline once, and you can deploy it for many, many data sources. And you will probably come up with new ideas of cool things we can do with schemas. So this is Schema Set. It's a project I've been working on for way too long. It's not released yet. We do have, so this schema representation, the derivation mechanism is finished. We are still working on migrations and evolutions. Yeah, just fork it and ask me anything about it. The code is slightly complicated, so what I do for wannabe contributors is I set up guided tours. So you ping me on Twitter, we set up a hangout, I will show you around the code. You will understand the code, and I will get new ideas. Everybody wins. And that's cool. So I'm waiting for you. And this project wouldn't exist without John the Ghost, who set up the ID, and without my good friend Dominic, who is my co-author and rubberduck. And that's it. I'm Valentin. I'm solutions architect at 47 Degrees, and we are always hiring. So if you're interested, talk to me. Thank you. And I think we have time for questions.
Hi, thank you for the talk. It was amazing.
Thank you.
I was wondering if, I know it's not released yet, but do you have maybe an example of like code in a more sort of a real project for this?
I don't have any, but maybe I can show you the tests. That's probably the only user of the code is the tests right now. So let me show you. So this is what it looks like right now. So this is the a schema definition, and maybe it's a little bit too small. Sorry. Oops. And yeah, the usage is really simple. It's the code that is complicated, but the usage is really simple. You just no, that's not a good example. Let's say, for example, JSON. So it's a little bit more complicated because we abstract over primitives and stuff. So yeah, there are more type parameters that we showed in the talk. But for example, you say, I have my schema. I want JSON reads in the Play API. What I need to do is just, take my schema and type 2 reads, and I get a Play JSON reads. And that's it. I don't have any concrete use, full-fledged application that will pick the version and find what reader to use. But hopefully, when it's released, it's that simple. If you use migration, there is a fair chance, I haven't measured yet, but there is a fair chance that there will be a compilation time penalty, because there are many things we need to verify at compile time, à la shapeless. So be aware that there might be a penalty. But otherwise, if you don't use migration, the compilation time will be just as usual, because everything, the derivation happens at runtime, at the beginning of your application. And overall, the objective is to make it very simple to use, slightly less simple to write your own derivation for your own type classes, but still pretty simple. I can show you how it looks. So this is a derivation. This is the power of recursion schemes. Here, I just need to say what to do with every node of my schema ADT. And recursion scheme will take care of the rest. But still, you have to think about all these terms, so you have to learn a little bit more about the API. And writing new migrations is the most difficult part. I won't show you the code, because you will have nightmares.
So that was a great talk. Are you depending on fixed point types?
So we have fixed point types, but because we are one kind higher, we have to define them ourselves. It's there. And this is where it becomes scary, because you see the types are a little big.
So you have your own fixed point?
I have my own fix, but it's exactly the same as the one you're accustomed with in Drosty or Matryoshka, but just the types are more complicated because it's one kind higher.
And you're using only catamorphism for this, because you need to only fold it?
Yes, we also have isomorphisms sometimes. For example, for JSON, you need an isomorphisms because our schema is able to represent, for example, anonymous tuples. And that's not really representable in JSON. So we have some messaging to do, and we do that with an isomorphism.
Yes, sometimes the evolution of recursion schemes is like you might need to go from fix and reach co-free. And at that point, your design can be,
it can get messy, and actually that's also why we used recursion scheme in the first place. It's to later be able to add the co-free, because that's the way we will implement customization of derivation. For example, what Cersei does by allowing you to snake case or things like that, that's the kind of thing we would need to have co-free for. Like tagging bits of your schema to say, or for example, the form and UI ID I mentioned, you would need to tag your schema with, for example, CSS classes. But that's not implemented for the moment.
Awesome, makes sense.
No more? Oh, there is a question.
Hey.
Hey.
So since you have your whole schema at type level, once you, I don't know, write the wrong function, does the compile error fill up, the screen twice?
At least twice. Yeah. Yeah, that's also one problem that will probably be there when we release the library, is that when it goes right, it's a bliss, but when it goes wrong, it's a pure nightmare, because basically the types fill the screen multiple times, even on John's settings. No more question? All right, thank you.